All right, nonlinear inequalities. So when you're solving these nonlinear inequalities, first thing you do is find your test intervals. So if you're looking at the formulas section of the notes, first thing I ask you to do is find the critical numbers. And this is where our rational functions are going to be equal to 0 or where they're undefined. So if you think about undefined, that's when we're typically dividing by 0. So we'll have a couple of those. And I'm glad we're using critical numbers as a terminology. You're going to use it next year a lot for various things. So getting used to this critical number talk, where's the function we're working with equal to 0 or where is it undefined? And then we're going to use those critical numbers to determine our test intervals. And then once we look at our test intervals, we can figure out what our solution is going to be. And we'll indicate these with interval notation and and a graph, a number line. So let's jump right into it. So x plus 2 and x minus 3. Our critical numbers would make this left side of our inequality equal to 0. So for this first quantity, x plus 2, if x were equal to negative 2, then that quantity, x plus 2, would be equal to 0. And the same thing here. If x is equal to 3, if we plugged in 3 for this in parentheses, that would produce a 0 right there as well. So now what we do is we take our quantities of x plus 2 and x minus 3, which, by the way, these are already factored, obviously, so that helps things. If they're not factored, you'd have to go through that process of factoring. But we list those quantities off to the left, and we make a number line underneath. And then we go ahead and we indicate on our number line our critical numbers, which we know is negative 2 and 3. And just like we did in the past, we're going to pick numbers within these intervals and substitute them in place of x and evaluate those quantities for those test numbers. So, for instance, a number less than negative 2 would be negative 3. If we plug negative 3 in place of x for the x plus 2, we would get negative 3 plus 2, which is negative 1. So, in fact, any number we pick to the left here of negative 2, when we plug it into the x plus 2, we're going to end up with a negative number. And that's what we're concerned with here. We're looking at the signs that we're going to develop of these. So, the only thing we care about is what the sign would be. So, you pick a number between negative 2 and 3, for instance, 0 would fall in this interval. If you plug 0 in for x, 0 plus 2 is 2, which is a positive answer. So we're going to have a positive number right there. And then if we picked a number larger than 3, say 4 or 5, if you put 4 in, 4 plus 2 is 6. If you tried another one, 5 plus 2 is 7. So in fact, any number you plug in is going to end up being positive. Then we'll do the exact same thing with our x minus 3 quantity. Pick a negative number like negative 3, negative 4, or a negative number less than negative 2 rather. And you plug it in for this x, you're going to end up with a negative answer. If you picked a number between negative 2 and 3, say you picked 1. Well, 1 minus 3 is negative 2. Since negative 2 is a negative number, we're going to indicate that with a negative symbol. And then our last one is a number bigger than 3. So you picked a number bigger than 3, say 4. 4 minus 3 would be 1. In fact, any number larger than 3 is going to yield a positive answer right there. And then, since we're multiplying these quantities, we're going to do the same thing. If you multiplied two negatives together, you would end up with a positive. I'm going to circle that one. So all the numbers right here to the left of negative 2 would end up being positive answers when we plug them in for x in our original inequality. And if you multiply a positive and a negative, you end up with a negative. If you multiply two positives, you end up with a positive. So now we have our number line drawn. So all we need to do now is look and see, well, the inequality we're working with for this particular problem is a less than symbol. So we're looking for numbers that are negative in nature. And we're not having a line underneath, so it's not inclusion, it's non-inclusive. So we're looking at negative 2 and 3. Our critical numbers are not included in this particular case. And the only interval right here that's negative is this middle section. So if we were to shade, we would shade that portion. And if we want to indicate that as an interval notation, it'd be negative 2 to 3. All right, so we've done problems like this. And make sure we have parentheses and not brackets, because remember, it's non-inclusive. All right, let's look at example number 2 and see how this one differs a little bit. So the first thing we notice in example number 2 is that we have three quantities now. So negative 5, 4, and -1 are our critical numbers. And we're dealing with a less than or equal to. So now we're going to have some potential inclusive answers on this particular problem. All right, and we're going to dive right into it. Come over here. We have x plus 5, x minus 4, and x plus 1. And those represent our critical numbers, our quantities for this particular problem. So now we're going to make our number line. And list out our critical numbers. So -5, -1, and 4. Now there's one thing unique about this one compared to our last problem, other than the fact that there's 3 quantities and a less than or equal to. It's the fact that we had this squared on the x plus 5. So we're going to do the exact same thing. We're going to list that square on our x plus 5 with our number line. And here's the reason why. Because if you put any number in place of x on the x plus 5 and you square it, it's going to yield a positive answer. So you picked a -6, for instance. -6 plus 5 is -1. -1 squared is 1, which is a positive number. So we know that this quantity would have a positive answer for numbers less than -5. And for that matter, it has a positive answer for every interval, because it doesn't matter what it's going to be, they're going to be positive answers no matter what we plug in for x. Okay, so now we can look at the -4. If you put the number less than -5 and plugged it in for the -4, on the -4 quantity for x, you would end up with a negative answer. If you plugged in a number between -5 and -1, say pick -2, -2 minus 4 is -6, so there's another negative. If you plugged in a number between -1 and 4, you end up with a negative. If you put the number after 4, say 5, 5 minus 4 is 1, so there's our positive. And then we'll do the same thing for the positive 1. All right, so we're going to have a negative here, a negative here, and then it finally becomes a positive. Once it goes past its critical number, it typically becomes positive. It's one little shortcut as you're kind of looking at these. Now we're going to multiply them. Well, a positive times a negative times a negative. Well, 2 negatives make a positive. So positive times a positive is a positive. Now positive times a negative is a positive. A positive times a positive is a negative. And then 3 positives make a positive. And we're concerned with only the part that's less than or equal to. Okay, so equal to means we may have some inclusive pieces here. So what would make this entire left side equal to 0? Well, that's our critical numbers. So we know that -5 would make that equal to 0. So would -1 and 4. And I found that when people look at their critical numbers and determine what's going on with those first, they tend to get the answer right more often. So we look at those critical numbers first, and now we look at any type of shading we can do. Since it's less than, we know we're looking for the negative portion, which is only the values between -1 and 4. And so now that we have that, we'll go ahead and list that in an interval notation or set notation as well here. So we know that -5, we'll just say that particular value is obviously a solution. And if we union that with all the numbers between -1 and 4, inclusive, that we have our solution set and written in interval notation as well for this particular inequality. All right, example 3. So remember, we had critical numbers. So we'll make this entire left side over here equal to 0. I'll put parentheses around this, as if x is -2. Now remember, the critical numbers also deals with undefined, and we do have a fraction right here. It's our first time we have a rational, because everything up to that point was the polynomials. It would make this, if x was 4, that would make us divide by 0 in the denominator, which is undefined. So here's our 2 critical numbers, -2 and 4. And we're going to do the exact same thing. We're going to make ourselves a number line. So we have, make this right here, x plus 2 and x minus 4 squared are our quantities. And our number line is -2 and 4. Sweet action. Now pick some numbers here. Number less than -2. We know that's going to be a negative. And then once we pass our critical number, all those values are going to end up being positive. And then here's one of those square problems again. Those are quick. We know that's going to yield a positive all the way across. And then a negative and a positive. If we divide them, because that's what we're doing on this problem, dividing, we end up with a negative. Two positives divided make a positive. A positive and a positive would make a positive. Okay, I'm going to go back up here and box this in. We're looking at those that are greater than 0, non-inclusive. So we know that -2 would make it equal to 0. We don't want that. We know that 4 would make it undefined, so we can't have that included within our answer. But all these answers in here would yield a positive inequality, and all the answers after our 4 would also yield a positive inequality. All right, so I'm gonna write our answer over here to the right, make sure it fits in our screen. -2, non-inclusive, to 4, non-inclusive, union 4 to infinity for that division problem. Let me just double check that recording picked up everything. Yeah, we're good. All right, example 4 has a little bit more going on. Before we can sit here and we can figure out what makes this left side equal to 0, we need to get our inequality equal to 0. So we need to take our 2 and subtract it over here and isolate or get everything to one side of the inequality and have the other side of the inequality having a 0 on it. So x plus 5 and x plus 3. Take away our 2, less than 0. Well, we want to get a common denominator. So we know we have x plus 5, x plus 3. And right now this has a denominator of 1. So if we were to write that, we'd have our x plus 3 on the top and on the bottom. So now we have a common denominator of x plus 3. We can combine that into one fraction. So x plus 5 all over x plus 3. So now we can distribute our -2 right here. So x plus 5 -2x minus 6 all over x plus 3. Come up here, continue our algebraic process here. So we know that x and -2x will produce a -x. And then 5 minus 6 will give us a -1 all over x plus 3. And one thing I should have been doing is I'm working this, and I apologize for it. I should have been carrying that less than or 0 all the way through. So we're looking for that portion to be less than 0. Now you can go about it from here if you want to. I think it'll be easier if we go ahead and take out that negative. So we're going to factor out the negative. All right, and then we'll divide that over. So now we're left with just x plus 1 and x plus 3. And the reason why is we're not having to worry about this negative, but as you guys have been drilled in the past, remember if you divide or multiply by a negative across the inequality symbol, you're going to have to flip that inequality symbol. So we went from less than now to greater than. Now we can go to our number line. So we would have x plus 1 and x plus 3 as our quantities. And we know that we have -3 and -1 as our critical numbers. And we start picking values here. We know that -4 plugged in would produce a negative, and then we would have another negative for values between -3 and 1, and then a positive after that. And then we have a negative here. We've now passed our critical number. So you can see that any numbers after x plus 3's critical number, which is -3, when we plug them in, would yield positive answers. two negatives divided would make a positive. We'd have a negative right here and a positive for all the values after -1. Okay, we're dealing with strictly greater than. So we know that we're not including our critical numbers. All right, and we're looking now, the only parts that are positive, because we're looking for greater than now, when we flip our inequality symbol. After we flip our inequality symbol, would be those. And then over here as well. So the final thing is just to make sure that we indicate that in our interval notation. So negative infinity to -3, union, and make sure that recording captures all this. -1 to infinity. There we go. All right, x squared plus 2x plus 1. Remember, if it's not factored, we need to. If you were to factor this, you would figure out it's just x plus 1 times x plus 1, which would be x plus 1 squared. So the only thing that's going to make this equal to 0 is if x was -1. So we have x plus 1 squared, -1 being our only critical number. Well, if you plugged in a number and you squared it, the only thing we're going to get are positives. And we're looking for only the pieces that are less than or equal to 0. Well, we have no spots that are negative, but we do have a spot where it's equal to 0, and that's at -1. So this is the one unique case, or this is a unique case rather, where we have one solution, and that is -1 itself. The critical number in this particular problem is the only piece that works. All right, example 6, do the exact same thing. We're going to have to factor it. So if you factor this, you notice it'd be x minus 2 squared. We're looking for where that's greater than or equal to 0. So we have one critical number again. And that would be the value of 2. Once again, it's squared, so the only thing we're dealing with are positives. And we look up here, it's a greater than symbol. Well, all the values are greater than, with the exception of 2, because 2 would make it equal to 0. So we're going to have an open interval right there on our 2. And we're going to be shading all of the number line with the exception of our open interval at 2. And then, of course, we need to make sure we write that in interval notation. So negative infinity to 2, union 2 to infinity. Of course, not including 2 in our answer. All right, example 7. First thing we do is try to factor it. We notice that we can't because the only factors of 5 rather are 1 and 5, and we can't combine 1 and 5 to get a 3. So we're still trying to find our critical numbers here. We can't factor, which means now we're going to have to do our quadratic formula in order to figure out our critical numbers. So we know it's the opposite of b being 3 in this case, so -3 plus or minus the square root of b squared minus 4 times a, which is 1, our leading coefficient, times c, 5, all over 2 times our leading coefficient, or a value, 2 times 1. All right, so we'll continue with our process here. We have our -3. This would be 9 minus 20 all over 2, or -3 plus or minus the square root of -11 over 2, which presents an issue, obviously, with that -11 right there. We can't have a square root of a negative number when we're dealing with the reals, which is what we're doing in this particular note set. So since that can't be the square of a negative, that means we have no critical numbers. So therefore, we have no critical values, no critical numbers. there's never a time where our inequality equals 0. So now we need to look at this inequality. And we need to figure out, well, if it's never equal to 0, and we can definitely tell, it's a quadratic, that means that when we plug in numbers here, they're either always going to be positive or they're always going to be negative. And you can quickly check that just by plugging in a couple numbers if you like. But you're going to see that x squared plus 3x plus 5 is always positive, no matter what particular value of x that you decide to plug into it. Even if you pick really large numbers, you think, well, I can make a really large negative quantity right here. Well, that really large negative quantity squared is going to be way bigger than 3 times that value. So this is always going to be a positive answer. Well, then we look at our inequality symbol. Our inequality symbol is less than, and since it's always positive, that means it'll never be less than 0. So this is a no solution. And if you want to make a number line for that particular answer, now you've done this before, the standard number line for no solution is just to indicate 0 within the number line, but shade absolutely nothing. So there's our no solution. And if you want to graph it, there's your number line. Last example, state the domain of our function. So if we're taking the square root of x over x squared minus 9, and we're dealing with the reals, we know that this entire portion underneath our radical, our square root, x and x squared minus 9, has to be greater than or equal to 0. So if it's greater than or equal to 0, we're looking only for those values that would make something not negative inside this radical, but it's okay if it's equal to 0. So we're going to do the same thing that we've been doing. We're going to find our critical numbers. So before we do that, we're going to factor the denominator. And notice that that factors as x plus 3 and x minus 3. This is the difference of 2 squares. So it looks like our critical numbers are 0, 3, and negative 3. So let me come over here to the side. I think it might be a little easier to see it that way. We have x plus 3, x minus 3, and x. I'll put it up here. Those are our quantities. And we have negative 3, 0, and 3 for our critical numbers. So you plugged in the number negative 4, for instance. That's going to be a negative, negative, and then once we get past our critical number, which our critical number associated with 0 is x, so this will become positives. Positive 3 right there. You plugged in a negative number right here. Once you get like to negative 2, for instance, it's going to become a positive, and the rest of those are going to be positive. And then our last one's negative 3. Well, if you plugged in negatives right here, and then finally we have a positives once we get past our 3 value right there. All right. So now 3 negatives are going to make a negative. Negative, a positive, and negatives make a positive. A positive, positive, and negatives make a negative. And then, of course, 3 positive make a positive. So now we have all these things labeled, and we're going to look back at our critical numbers. Our symbol is greater than or equal to 0. And we have to be careful on this one. So it's easier to think, well, it's greater than or equal to 0. Since it's greater than or equal to, that means all of our values are included. Our critical numbers are included. But that's not the case in this problem. 0 is, because if you put 0 in for x, there's no issues. You're going to have 0 in the numerator. Of course, that would make this entire left side equal to 0. So I'm going to go ahead and go over here to 0 and put a closed circle on it. We are going to include that one. But negative 3 and 3 are different. They're in the denominator of our rational function over here. We do not want to divide by 0 because that would be undefined. So negative 3 and positive 3 are not included in our solution. So then it's a matter of just shading. Well, we're looking for greater than. We're looking for it's positive. What's positive right here? So we can shade that portion. And it's positive for all the values after our final critical number there, 3. And then it's just a matter of filling that in. So we know that -3, non-inclusive, to 0, inclusive, is part of our solution. And then, of course, we're going to go ahead and union that. Don't include the 3. 3 to infinity being our final portion of our solution. There we go. Boom, bat. There's our answer for our final example. So hopefully this is helpful for you. If you have any questions, let me know. And you should see all this stuff posted momentarily. And if you haven't seen it, the homework associated with this lesson is not due until April the 7th. You guys have a good one.